We'll start off with some news that's going on right now. Samurai. DOJ just arrested a few of the co-founders of Samurai. Samurai is a mixing service, and they basically valued privacy for your coins. If you wanted a coin join them, so your UTXOs weren't as visible if you bought from a KYC source. I mean, I think privacy is a right for everybody, and I think what DOJ is doing is setting a pretty strong precedent in going after developers. And I changed the link. Money laundering is legal if you're a big banker. I mean, uh, plenty of instances. They all get away with fines. And it's a little double standard. Second one's a little more ridiculous. The fourth epic sat, if you subscribe to ordinal theory, just sold for $2.1 million. So the fourth epic sat. So there's epochs, and that's Bitcoin's issuance schedule. So we're just entered the fourth epoch. And the first sat, just one sat, sold for 2.1, auctioned via BTC. You can't help yourself but laugh. That doesn't make a whole lot of sense. I'd be curious to see how the return on investment will happen over the next few years. And even more crazy, the original Buy Bitcoin sign. You saw this young man held behind Janet Yellen in 2017, sold for less. A physical item sold for less. Anyways. And Coinbase launches Pepe perpetual futures because we all need more shitcoinery and gambling. So without further ado, let's have Nathan introduce our guest speaker.
Yeah, so this is Tyler here. Most of you guys in here know him. I don't know if you guys do on the Zoom. He has a background. He's a thermal engineer. He studied mechanical engineering at the University of Wisconsin-Madison. Came to Colorado as a rocket thermal analyst in the aerospace industry. He left his role as a defense contractor to pursue Bitcoin. Thank you. And he's also the founder of Exergy LLC. So without further ado, Tyler, thank you very much.
Yeah, thanks everybody. I know most of you here are all Bitcoiners. You know a lot of stuff already. But I'm kind of going to walk through things from a beginner level just for the recording as well. I think it'll help tee things up a little bit here. So nice to meet you all if I haven't met you. Thanks for introducing me. And I'm touching on Bitcoin and thermodynamics, and what has become my obsession is heat reuse and how Bitcoin mining is a value add to society, not something to be worried about. So the outline here, I figured we'd go into a little bit of a Bitcoin refresher. I thought there'd be some novices in the room. Doesn't seem like that's the case, but I'll still talk through it just for my own benefit here, if you guys don't mind. We go into network defense, how it ties to energy, and then the outcome of all these things combined. So for the Bitcoin refresher, we're all pretty much aware that Bitcoin has a fixed supply of 21 million. There will only ever be 21 million, and those are issued programmatically to be controlled fairly, and it's a deflationary issuance schedule, right? So we know that there only will be 21 million. It's controlled through the halving cycles, and that those block subsidies where new coins are issued decay over time. And because of that fixed supply, it's a store of value and a unit of account. So you have this demand supply ratio, right? And now you have a fixed denominator. The supply is fixed. So that is a great store of value because you can't increase the supply. And then also it's the perfect unit of account because the ruler is no longer changing length, right? When we measure things in dollars, what does that even mean? Because the amount of dollars changes. So how can you measure the cost of things? It's totally manipulated. You got two knobs you're turning here. It doesn't make any sense when you really think about it. And then also touching on the decentralized ledger. So Bitcoin blockchain is decentralized and it cannot feasibly be altered, falsified, or deleted. And then for a newcomer, they say, well, how is that possible? So I'll kind of outline that here. So this is that supply issuance cycle. It's just a summation equation, 210,000 blocks, that's a 210,000. And then 2 to the I is your halving epoch. There are 32 halving epochs. And you start with 50 Bitcoin issued every 10 minutes in each block, and that keeps getting divided by 2, right? So we just had a halving event where we went from 6.25 Bitcoin issued every 10 minutes with each block to 3.125, and that will asymptotically decay to 21 million. Bitcoin versus crypto. I know the first time I was here for this meetup, there were some crypto guys in the room, so I thought I'd like to touch on this. So what's the difference, right? It's Bitcoin, not crypto. Why Bitcoin, not crypto? So Bitcoin is fairly distributed, as I outlined with that halving cycle. There was no like initial coin offering, or, you know, I set a couple of coins aside for me when I started, right, before we went live. Satoshi didn't get a certain amount allotted to him when he mined those first million Bitcoin. He had to expel energy to do so, the same as anyone else. You could have logged in to the protocol, you could have downloaded the protocol, started doing it at the same time. So it's fairly distributed. It's easily decentralized. That has to do with the size of the blocks, right? So it's feasible for me to buy a Raspberry Pi or an old Dell Optiplex and a terabyte hard drive and say, you know what, I'm going to store the whole Bitcoin blockchain. I think it's 600 to 700 gigabytes right now. So because it's defined in that manner, it's actually feasible for us to keep up with the blockchain as it grows, with hardware as that progresses as well. There's no central authority versus sometimes there's a central authority like the Ethereum Foundation, right? So it's, if I were to attack Bitcoin, like who do I call, right? Who's the CEO? Who do I get to come and say, hey, can you change this for me? Well, there is no person to change it. And so, excuse me. That last point there was just proof of work. And there are some crypto assets that are proof of work still. Is Litecoin still proof of work? I can't even name 5. So, but most of them are transitioning to proof of stake for reasons they claim have to do with the environment or efficiency. Fake claims, in my opinion. So how does it work? I tried to summarize this into 7 bullet points that are simple to understand. So every node has the same copy of the ledger. An analogy I like to think through for this is, it's a giant Excel. What's up, Matt? It's an Excel spreadsheet that tracks every single coin, UTXO, every address that owns every coin. And then everyone has the same copy of this Excel ledger, right? And you have keys that can move your coins. And everyone is in agreement. So there's consensus. Everybody has the same copy. And when you send a transaction, your node, your wallet software communicates with the node to send this transaction, and it gets broadcast around the network to all the other nodes. That's through something called the gossip protocol. It happens in seconds, and within a minute, your transaction is seen by all the nodes in the network. And then miners put those transactions into block templates. They do this right now based off of a fee system. So it's kind of like you got to pay the bouncer to get into the bar, and if you pay more to leap that line, you get to the front, and they'll let you in next, right? So that's what the miners do. They put these transactions in block templates, and then those block templates are mined through either solo mining, where you're essentially mining yourself. You're not in a pool. You're kind of just rolling the die, trying to win this block by guessing a low enough number with the nonce. But most mining happens through what's called mining pools, where everyone kind of looks at this block template. This is actually a contention point right now in Bitcoin mining, where the pools are orchestrating these block templates. So they are piecing together all the transactions. Okay, these ones are going to the next block. These are all the guys paying the highest rate. And then they send that out to their mining pool, and those miners all hash. They all contribute their work, their energy to guess the nonce and adequately solve this block. Caveat there, a little tangent. So the problem you may see is, well, who gets to make the block template? And if it's big mining pools that are centralized or all owned by one authority or one master LLC, you kind of get to centralize and audit control what goes into each template. So you can control it, you can censor people, right? Anyways, so after the miners put in the energy, they consume energy to confirm blocks. Those are now confirmed on the blockchain, and that updates the ledger. So now there's a new block. There's a new block height. The source of truth is the longest ledger, right? So you're adding blocks to this blockchain. The longest ledger has the source of truth, and that is communicated back to the node. So everybody's node at home with their copy of the ledger is updated, and then that process is rinsed and repeated. So then you just continue to do that, and that is how the blockchain works. So I'll go into network defense. Like, how would you attack this? How do I know it's not, how can it not be hacked, right? So nodes do the verification. They make sure that you're meeting the rules. So if each node has a copy of the Bitcoin protocol rules and a ledger of all the transactions to ever exist. So if I tried to send a transaction that said, you know what, I have 2 more Bitcoin than I actually do, the node would weed that out and say, nope, you don't. Or if you tried to change the rule set with oh, there's 42 million Bitcoin according to my rule set, right? You'll actually be blacklisted by the other nodes in that gossip protocol that they communicate with. So you kind of you're forced to play by the rules. The miners then confirm those transactions and assign new ownership of coins, updating the blockchain with new blocks. And mining, that process costs energy. And the whole point is, to execute these updates to the ledger, there has to be a proof of work involved. There's no free lunch, right? You can't just say, oh, I deem by fiat, by decree, that now there are these coins here and these coins here, and you get this and I get this. No, you have to put in the work, just like if you were mining gold in the Colorado Rocky Mountains, to find the new money or move money around. And these blocks are chain linked. So the key point here is, each block is hashed with the previous hash of the block before it, and that creates this link. So if I said I want to falsify a transaction that's 1 hour old, these blocks are mined every 10 minutes, that would require 6 blocks worth of work. So you would have to redo an hour's worth of work, and I'll touch on after this the amount of energy that goes into that. You have to redo all that work before the next block is found, because remember that the longest chain is the source of truth, and say, okay, I redid this block, this block, this block, this block, and this block, just to change that one transaction that was an hour ago. And this is the new copy, okay? I hacked the network, right? And you have to do all that before the next block is mined by some other actor. So that's a defense mechanism of the network. And that energy, that link to energy is what makes it infeasible to really attack the network. So here's an image I screenshotted last night from Hash Rate Index. This is the total network hash rate. It's a 7-day moving average since 2009, so since inception. We're floating under 700 exahash right now. And what does that mean? What's a hash rate? So a hash is just one computation of the SHA-256 hash. That is the process that miners compute to guess a nonce. I'm getting a little in the weeds here, but effectively guessing a low enough number that meets a difficulty criteria. And when you meet that difficulty criteria, you meet the threshold to mine the next block, and you get the Bitcoin reward. So what I'm showing here is just how much work is behind it. I think exahash is quintillion. Is that? I think it's 700 quintillion guesses per second. It's astronomical, enormous number of guesses per second. And so how does this tie into energy, right? So as I've outlined with the network defense, to attack the network, you essentially need to mine the blocks and alter the ledger in your favor before the next actor. And to do that, you would need 51% of that network hash rate, that's 700 exahash. You need 51% of the hash rate to have higher odds of verifying your transactions with your block templates before other parties. 51%, you just need a majority. So say it's 350 exahash. If we were to assume right now, this is not true because there's a variety of different Bitcoin miners and machines and energy prices that define the network. But let's just say the whole thing was running at the new industry standard of the Bitmain S21 Pro. So that's an industry leading miner. It's around 15 joules per terahash. That means it takes 15 joules of energy to compute 1 trillion hashes, 1 trillion guesses per second. So very efficient, super efficient. That machine consumes 3,510 watts constantly. It costs $6,318 per machine. And if I assumed an energy price of 3 cents per kilowatt hour, for reference here in Denver, I pay 13 to 14 cents per kilowatt hour. I think the global average is around 14. So this is extremely cheap energy. All of these conservative factors, it would take 7 gigawatts of energy for a 51% attack, assuming everyone was on these new efficient machines. It cost $9 billion just for all those machines alone, $150 million an hour in electricity at that conservative rate. And these are astronomical scales where, you would see trends in the copper markets, the silicon markets, the chip manufacturers, the TSMCs, the Samsungs, right? I mean, you would be able to observe this attack coming before it even manifested. So that addresses a little bit of FUD there. And so you may say, wait, that's a lot of energy. Bitcoin uses a lot of energy. That's a talking point of a lot of hit pieces. Oh, Bitcoin's going to use as much energy as some small European country, whatever. And they get all up in arms about that. But we have to remember that's a feature, not a bug. So exactly, it uses a lot of energy. That is the defense mechanism. That's what roots Bitcoin in the physical realm versus things that are fiat, that are by decree. So it's a feature, not a bug, because Bitcoin energy consumption is required to modify the ledger. It's highly resilient, right? It would take all of that work and effort to falsify it. It would also be against the actor's interest to do that, because if you did 51% attack the network, it would then be compromised and its value could tank. So you're incentivized to not want to attack the ledger, the network, and also it's at this point deemed unachievable. Another thing I want to point out here is Bitcoin's an apex predator. So because of all that energy consumption, you know, it's a truly capitalistic market. How can I be as profitable as possible? You have a bunch of operating costs. The primary operating cost is your energy price. So it costs energy to mine these blocks, which are your income, your rewards. You're subsidized Bitcoin every 10 minutes, and then the transaction fees associated in those blocks. So that's your income as a miner. And you want the cheapest energy because that's your profitability. So Bitcoin miners are forced to find the cheapest sources of energy. It's an apex predator in the sense that, you know, people say, oh, it's bad for the environment, it consumes a lot of energy, it forces this, forces that. No, it forces smart individuals to find innovative ways to use and monetize the cheapest available energy on the planet. And then there's some additional benefits. And this is kind of where I'm transitioning into what I'm interested in, what I want to talk about. So that is scalable load on demand, heat reuse, which is a huge passion of mine, and then off-grid waste energy. So what's the outcome of piecing all this stuff together? So there's power generation plants. These create electric power that we use on the grid today. There's also off-grid, and they generate electricity at huge scale. And part of that is the way the economics play out is, okay, if I undersize it, then I get brownouts, I get blackouts. That's a bad scenario. You don't want your power generation to be undersized. But for these power providers, if you oversize it, right, such that, say you double the size of the power generation capacity of Denver or Colorado, the economics don't work out in their favor from the capital expenditure required to build out that infrastructure. And they can't always sell that energy, right? It allows growth, but what's the long-term return? Is it in their favor to do so? But now, for the first time ever, you have a powered eater. So Bitcoin miners are essentially an inverse power grid. They're the opposite of a power grid. They consume energy on demand, no matter what, whenever. They can also shut off at the flip of a switch. It's called curtailment. So now, say you were to combine those two items on the left there, you have someone who can create power, and then right on site, you can consume any excess power that's not sold and instantly turn it into money. You know, you could build a Ford power plant or a Ford factory, you could sell cars, you could hire a bunch of people, a bunch of engineers. You do all this stuff to turn that electricity ultimately into money, right? Into economic prosperity. But there's all these intermittent steps. Sometimes it's not feasible over long distances to transport that energy. Sometimes it doesn't make sense for the power company to build out all that infrastructure, but now you can essentially attach these two cycles, combine them, and whenever there's excess generation, the power generation can sell it to themselves. They can just monetize themselves all that excess capacity. And then when the grid needs demand, say it's a cold storm or a hot month in the summer where everyone's turning on their AC units, you can just ramp down those Bitcoin miners very quickly. There's not much inertia to these machines, right? If I had big steam power plants or big rotating motors and generators and turbines and presses and all this manufacturing infrastructure, these are enormous machines, right? There's an inertia to them. You literally can't just shut them off and flip a switch. There's a time decay to this, right? Before that power can ramp down. Not with Bitcoin miners, they're electrical machines. They're just computers with chips, and you can just basically flip them off. You need to be conscious about thermal cycling them and not shocking them. But when you do novel workarounds for things like that, you can essentially just turn these machines off and kill power. So you can turn on and off power extremely quickly. And that has created a market of curtailment that is very, very exciting to the power generation facilities. Networks like ERCOT in Texas, their grid, and then TVA, the Tennessee Valley Authority. I mean, they're closely working in collaboration between the power generation and the Bitcoin miners to basically, it's a new product that's entered the market. To the power generation guys, there's never been something like this that you're like, wait, I can just consume, you guys can just take all my excess power whenever you want, and I can just turn it into money right there on the spot. Yeah. And now I'll go into stranded energy. So what this also allows is monetization of energy resources, natural resources that are otherwise stranded, physically stranded. I mean, there's natural gas wells up in Wyoming where it's in the middle of nowhere. There's not big towns. It's too far to pipe it or send it elsewhere, right? You can now just plop a generator, genset. That's what you see there in that picture. That's Upstream Data, their company that Adam works at, Adam O. And they turn that natural gas into electricity with a generator. It's just a combustion cycle. It's an engine. And then they use that electricity to mine Bitcoin. This is great where you would otherwise flare natural gas, which is demonized. It's also regulated, heavily regulated in many jurisdictions. And then also, I mean, truly a lot of people that are drilling for oil or whatnot, they have natural gas. A lot of times they cap their wells because they can't feasibly use that energy, monetize it in any other way. So it's a new tool in their toolbox to monetize stranded energy. And then finally, there's heat reuse. So this is what I'm going to touch on a little bit more here. So there's a one-to-one relationship of electric energy input and heat energy output. It's not like any of it's created or destroyed or lost. If you got a 1 megawatt mine, it uses 1 million watts of electricity coming in. You have 1 million watts of heat to dissipate. And traditionally, the current state of the industry is, oh, okay, we got to cool these machines. There's some parasitic losses for running pumps and lights and coolers and whatnot. So just under 100% efficiency, but nearly there. You have a lot of cooling. So my thought is, what if you can reuse this heat energy as another method to subsidize your economics and to ultimately benefit the Bitcoin network in a distributed way? So my thinking is that heat reuse is the future. I think it's going to play a large role in the upcoming halving cycles. And so as I said, miners convert 100% of electric power consumption into heat, and that heat can be properly captured and transferred and reused. There are infrastructure and a lot of work has gone into how can you move heat around. That was my background, heat transfer, thermodynamics, energy systems. How do you move heat from here to A to B, right? I need it not here, I need it there. And because you can monetize that waste heat, you can actually introduce a new method to stabilize mining economics and offset utility costs. So I'll touch on that a little bit more detail. And then finally, heat reuse, I think, helps incentivize for more decentralized mining. You can now have mining in sites that you wouldn't traditionally have them. And also you're less sensitive to having the most efficient machines or having the cheapest power costs if you're able to monetize that heat. If that heat is sold as an additional source of revenue stream, then you don't have to always say, you know what, I need the newest machines with the most cutting edge hash rate, because you have another source of income. So this is an energy balance equation. The sum of energy is equal to the internal energy, the delta of energy between a system is equal to the delta of the internal energy, kinetic energy, and potential energy. And so the first law of thermodynamics is just that you can't create or destroy energy. It's the quantity is always fixed. Your in is equal to your out. It just is transferred into other forms. You're not creating it. You're not destroying it. All of it is just moved between different forms. There's potential energy, like gravitational potential. There's electrical energy. There's heat energy. There's nuclear energy, all these different forms, right? And then the second law states that entropy increases for all spontaneous processes. And that sounds confusing. It's like, what is that? The best analogy here is like, okay, you put creamer into your coffee, right? It's going to dissolve and diffuse. How much energy would it take to atom by atom separate the creamer from the coffee, right? And the point of this analogy is saying that all systems tend toward disorder unless you put work in to reverse that process. So there's a directional nature to the universe, right? That's the chaos. That's entropy is always increasing. So if you combine these two things, you have quantity and quality. The quantity is conserved, the quality is not. So if you have 1 megawatt of electric energy from your Bitcoin mine, you have 1 megawatt of heat energy that you got to dissipate. But you can do a lot with that quality of electric energy. Electric energy is high quality. You can charge your Tesla, you can charge your phone, you can run a Bitcoin miner, power some lights, play a speaker, all this stuff. But when you have 1 megawatt of heat energy, how do I charge my Tesla with that? What do you do? That is a low quality, heat is a low quality form of energy. And so there are thermodynamic cycles where you could take heat energy and convert some of it back into electricity. without getting too into the weeds, it depends on the temperature difference between the two. So the delta T defines that energy you can convert back. I ran some quick calcs. You can find a thread on my Twitter, but if you had 1 megawatt of heat from a Bitcoin miner, 80 degrees Celsius is about the peak output temperature. And then to your ambient temperature where it's 20 degrees Celsius, 70 outside, right? My math showed that you could only, convert 90 kilowatts, so 9% of that 1 megawatt back into electric energy. And that was assuming perfect conditions. That's called an exergy analysis. So exergy is kind of the inverse of entropy. Entropy increases, tends toward disorder. You want to maximize your exergy, so your useful work. And so the thought here is, well, okay, it's not really feasible. It requires all this machinery and thermodynamic cycles to turn this waste heat back into another form of high quality energy that I can use for other things. But what if the heat is desired for itself? What if you just want to use the heat? Then it doesn't matter that it's low quality energy. It's just a useful form of energy for that application. And that's kind of what I'm focused on here. So here are some applications of heat reuse that are either already happening with Bitcoin miners through a lot of tinkerers and nerds and plebs out there, or future applications that I see as feasible. So on the upper left here is a greenhouse. There are some Bitcoin greenhouses that grow food. They dry food. I know they dry food in Africa with Bitcoin miners, that hot exhaust air from an air-cooled Bitcoin miner. Greenhouses, a lot of that in Colorado. In the middle here on the top, that's actually my personal S9. It's an older Bitcoin miner. It's not efficient by any means. It's not profitable. It doesn't mine me more Bitcoin than the cost of the electricity that I spend on it. But what it does is it's basically a space heater that I can dynamically control with firmware up to 1400 watts, which is a lot. I blew a fuse in my apartment when I was tinkering with it. So I've downclocked that a lot to 400 watts, and it's an excellent space heater. I put some quiet fans on it. It's slow. It's not too noisy or anything. And that, with my 13 cents kilowatt hour electric power costs, where I live in Denver, that cost me about $1.30 to $1.80 a day to run. How many days of the year are you running a space heater, right? It's usually a plug it in when you need it type thing. But it mines me, 25 to 50 cents worth of Bitcoin a day with its current efficiency, less now that we just had the halving. So it's subsidized, right? It's literally no different than a resistive space heater. A resistive space heater, all they do is they convert electric energy into resistive energy, friction. Yeah.
Is there a difference in the quality of heat, like the temperature you're able to get out of a miner is a lot less than, let's say, a wall heater or some sort of higher heating application? Because you can't push them to that level where you get that high quality heat.
Great question.
Yeah, because they're not, the components aren't to that level yet, but you
Yeah.
potentially use like water heater or like a boiler type application. But it's not that level yet because you can't push it that hot.
100%. So the higher the temperature, the higher the quality, for sure. All you need to drive heat transfer is to have a temperature differential. So heat will flow from hot to cold because of that second law, that directional nature. So as long as you have any temperature differential, you will have heat transfer. And the higher that temperature differential, the more heat transfer you can get. So I do argue that. I had a blog go live with Brains yesterday where I'm basically arguing for higher temperature chips, kind of designed in hash boards that
replace like boilers and like
exactly
furnaces.
exactly.
Like it's warm, not like
you are certainly limited in the use cases by the throttle temperature limits of Bitcoin mining machines. Yes. So great question. But for the sake of heating my apartment, yeah, it's perfect, right?
Greenhouses, that's a really good one.
Exactly.
Like a solid gold PCB board.
Yeah. So I was touching on resistive heat, right? So it's literally just friction at the atomic scale. You've got electrons flowing through these copper traces, creates friction, vibrations at the atomic scale, and it becomes heat. So that's that transition of electric energy to heat energy. And it's no different than a space heater you would buy at Harbor Freight or Home Depot and plug into your wall, one you buy on Amazon. The trade-off here, I like to call it a double spend, is I'm getting an electric heater, it's resistive heat, same thing, but it's also computing logic in the background. And that logic, every now and then, mine's a block, and I get subsidized with a block reward. So I get Bitcoin to electrically resistive heat my apartment. And so these applications can manifest into much bigger systems. And this is kind of what I'm all envisioning here. So on the top right, I'm not aware of anyone that's actually executed this. That's a giant industrial absorption chiller. An absorption chiller uses a heat load to drive a thermodynamic cycle to provide a cooling load. You guys have refrigerators in your air conditioners in your car, in your apartment. Yeah.
Yeah, the one on campus I've worked on that feeds this campus over there.
There is an absorption chiller on campus?
Yeah,
That's fantastic.
which is just been real upgrade on that one.
I need those are people I probably need to talk to then. Okay. Yeah. Yeah. So a typical refrigeration cycle uses an electric motor, a compressor. It spins a pump, pressure differential, and that drives the cycle. It moves this refrigerant around, and it's like a heat pump in reverse. And you're able to you put power in, and it takes advantage of the temperature difference between your zones, and it provides a cooling load. An absorption chiller is the same thing, except instead of plugging in a motor with a compressor and a pump to drive that cycle, it's using the temperature difference of the heat in the working fluid to drive the thermodynamic cycle. They're typically less efficient than a refrigeration cycle. Their performance is not as good, meaning you get, like with a refrigeration cycle, you get around, if you put in 1 watt of electricity, you get around, the good ones, 4 watts worth of cooling. So it's called a coefficient of performance. It's 4 to 1, it's great. But an absorption chiller, it's less, like 1 to 2. And so they're often used in industrial scale. This is a huge image of one. I don't know where that is, but in scenarios where you have waste heat, free heat, it could be a steam power plant, it could be a power generation site on the earlier slide. Anywhere you have free heat, you just pump it through a heat exchanger, you run the cycle. Say you've got a big manufacturing plant, like a car plant like I described. You know, there's a big factory building cars. They have all this machinery that exhausts a lot of heat. What if you capture all that heat, transfer it, run it through the absorption chiller, and then you duct it and you cool the manufacturing plant where your employees are working. So I think it makes a lot of sense, and I know there are people starting to brainstorm, okay, what would it take to have miner waste heat, especially on the large mega mine scale where you have megawatts of power, to run this thermodynamic cycle where you're just pumping that waste heat to provide a cooling load. The caveat here for absorption chillers, I've done a little bit of research, had some calls with like Johnson Controls and whatnot, and it tends to be that they require like an 80 to 100 degrees Celsius input temperature to drive that thermodynamic loop. It uses ammonia, specific working fluids chosen for their properties in the temperature differential to drive that cooling cycle. And with Bitcoin miners, on the high end, you see an output temperature just beneath that 80 degrees C range. So there isn't perfect overlap right now. And I think that is a great case for, you know, chips that can run a little hotter. So you can get that delta T and then use Bitcoin miners in a cooling scenario. So that's something I'm very interested in, but I haven't seen it manifest yet. On the lower left there, it's cut off, but that is a distillery. So that's a bourbon distillery. They pay for heat. Same thing with beer breweries, right? So anyone that pays for heat, why would you do this? Why would you do it in a manner that doesn't subsidize you with Bitcoin mining rewards? There's a pool heater here on the left as well. So that's just a traditional pool heater. There are already pleb miners that are, you know, hacking together and modifying some old Bitcoin mining ASICs and putting them in dual loop systems where they transfer that heat from the miner to a fluid. That fluid's usually oil. It's like an immersion bath. That's actually what this image is here to the right of it. So that whole miner is submerged in immersion fluid. Does a good job of capturing all that heat. It can transport it well. It has what's called a high specific heat capacity, which means it takes a lot of energy to change the temperature of that fluid. So if you move it far away, it doesn't lose its heat energy very rapidly. It has a lot of mass or thermal inertia. So then you would take that immersion fluid, that's your first loop. You can connect that with a heat exchanger to another liquid loop that runs your pool water, right? And you're essentially just transferring the heat from its electric energy, goes to the miners, vibrations, it turns into heat energy. That heat is transferred to this oil. That oil goes through a heat exchanger to water, and then it's in your hot water in your house. It's in your shower. It's in your pool or whatever. That is an application here. And then finally on the right, this is an industrial scale dry cooler. So the colloquial term is dry coolers, but what they do is they take these liquid loops, either from the oil or the water glycol mix, and they run this through large heat exchangers that are intended to transfer that heat to the air. And so they're giant tube and fin coils where the fluid runs through these copper tubes, and there's tons and tons and tons of fins, just like the radiator on the front of your car. And what those fins do is If you add up, imagine all the surface area of all those fins, it's tons of surface area. So you want lots of surface area because that's what your air is passing through, right? It's hot surface that the air is then convecting with. And that distributes the heat to your environment. There's fans on the top of them that are used to control how much flow rate of air flows through them, and that can control how much heat that they exhaust.
There's some really massive ones across the street.
Yeah. So
The size of multiple of these rooms.
university campuses are a great point, and a great example of, I think, a future applications for Bitcoin mining heat reuse, because they often have like steam power plants that heat campus, or centralized water heating, absorption chillers, like you just mentioned, dry coolers. So there are a lot of applications for localities where they have heating systems that are meant to distribute heat over a wide variety of buildings and use cases. And if you just introduced Bitcoin mining, you could solve a lot of problems. You could be load balancing on the grid. It could distribute heat. It could monetize or subsidize those heating costs. There's a lot of benefit. Yeah, so why would you do this? There's kind of three scales and applications of Bitcoin mining, right? There's the mega mines, the riots, these companies that have millions and millions of watts, megawatts in the middle of nowhere, Texas. They got cheap power, huge, giant, they look like power generation sites, giant warehouses and containers with thousands and thousands of machines. What value would heat reuse offer these guys? I mean, the absorption chiller could be used to cool their facility, right? Otherwise, they'd be spending that electricity, some parasitic loss to run those AC units. You could also see, I think, symbiotic relationships where you have power generation and the large miners combining in a symbiotic relationship where they offer value to one another. But also these large sites could, be set up in collaboration with manufacturing processes for people that pay for heat year round. Then go one step down the line, you have like the manufacturing operational scale. So not megawatts, but a project that I'm kind of chatting through right now with some folks is up in Minnesota. It's they're using solar, and then they have cheap blended electricity costs. And then instead of batteries or selling the excess power back to the grid, they thought, okay, let's install Bitcoin miners to kind of flatline our load curve. You can ramp those up and down and kind of have a nice even consumption throughout the year, depending on the ambient temperature and the conditions and the grid demand. And that's desirable to the power generation site. So the people that sell electricity in Minnesota, they like a customer that's like, oh, you charge us $5 a day. You're very predictable. I like that. You're kind of flatlining the load demand. That introduced Bitcoin mining into that mix. And then we also thought through this, well, you guys are in northern Minnesota. We ran some numbers. It's a 150,000 square foot warehouse. They spent $60,000 last year on natural gas just to heat the warehouse so their employees were comfortable. You plug a 500 kilowatt Bitcoin mine in there, so small compared to these mega miners, but large compared to my home space heater. And what that would do is you essentially, with that scale, 150,000 square feet, 500 kilowatts, you could get 80% of the heating demand on the coldest day. And if you ran those numbers, you could probably cut 60% of the heating bill cost. It would cut 60% of the natural gas cost that they pay as just an operational expense for their heating for the comfort of their employees. And now that is just a byproduct of the load balancing feature that they added to their facility. So there's all these cool applications, and what I see as like these operational and manufacturing scales where, you are already a large power consumer. You may pay for heat year round. That's kind of a key. You want to find people that are paying for heat year round. And then how can you subsidize that with the Bitcoin mining rewards? And then finally, there's the pleb miners, the home miners, and people like me, my space heater. It's not as desirable in my opinion. It's still awesome when I need it, but I'm not paying for heat year round. I don't pay for it 24/7. My space heater is only when it's cold. So there's that whole side of things. Your home heater, how often are you paying for heat? Maybe if you run a hot tub year round, there are applications at small scale. So that's just the breakdown by scale. And the breakdown by economics is you can subsidize your electric costs that you would electric or natural gas costs you would already be paying for heating, or for just the traditional miners that are only mining. This is, I think, something that's key with economics. You can offer a predictable, flat baseline of revenue stream for the mega miners. So I touched on at the beginning in the overview, the refresher, we're transitioning through these halving cycles from block subsidies being the majority of your Bitcoin mining rewards. So it just went from 6.25 to 3.125. We're transitioning to that majority will eventually be transaction fees. And what does that mean? Well, block subsidy is predictable. I know for years that the block subsidy is going to be 3.125 every 10 minutes, right? But eventually that number is going to be basically zero. And all of the reward, the Bitcoin mining reward, will be transaction fees, which are by definition variable. It has to do with the traffic of the network throughput. So if you say, okay, well, now my profits are going, I know for a fact my profits are going to be more volatile in the future. What can I do to set myself ahead of the other guys? You could sell the heat for a fixed cost because you know no matter what the transaction fees are, no matter what's going on with the network, you're always going to be converting 1 megawatt of electricity into 1 megawatt of heat. You just got to find some guy that will pay you X price for 1 megawatt of heat. And now you have a baseline revenue stream that can help offset this variability. And then the last thing I wanted to touch on here was decentralization. So because of those incentives of subsidizing your costs or offering an additional revenue stream, I think that it offers a method for Bitcoin mining to be less sensitive to efficiency. When new miners come out on the block, you know, everybody's got to transition to the newest machines to remain competitive because it's ruthlessly competitive, right? It's that capitalist market. You also have to be aware of your power costs. So there's power contracts, which I'm trying to learn more about still, but these guys, these big players, they map out many year deals to lock in pricing for electric because that's their biggest operating expense. They are super sensitive to the cost of electricity. But if you have another revenue stream of selling your heat, you are less sensitive to these other variables, and it affords you the opportunity to outcompete, I think, your competitors. So I think mining for heat and monetizing that heat will become more necessary than ever to remain competitive, probably in the next few cycles as we transition to transaction fees being the majority of the block reward. So what's required to get to this state? I talked a lot about, okay, you can do this, this, and this, but there's a lot of work that needs to be done in the middle. Obviously, we're all here today, just listening to my talk. I appreciate that. So education and awareness, spreading the word, defeat the FUD. So Bitcoin mining is good. It's an apex predator that hunts for the cheapest electric power. It's a way to monetize wasted energy and all these good things, right? And ultimately, I got to throw this out there, but energy consumption is good. When there are no such thing as wealthy countries that consume little amounts of energy. So when someone tells you to stop consuming so much energy, they're telling you to be poor. Energy consumption is good. We need to produce as much energy as possible. There's essentially infinite energy. We have infinite access to energy, and we just need to use technologies like Bitcoin to capture it and distribute it to humanity. And then open source miners, I think, are important. So right now, there's two main manufacturers, MicroBT and Bitmain. They're both Chinese companies. They make all the miners. They're closed source, which means if I wanted to make a Bitcoin miner that was a hot water heater in my house, right? Right now, you have to get Bitcoin miners, put them in a tank, get immersion fluid, get a heat exchanger that transfers the heat to the water, be a tech wizard, figure this all out, tie it to your thermostat in your house. You want to use your Google Nest, whatever it is. There's all this difficulty introduced because these miners are closed source. You can't really look at how the circuitry is laid out or how to communicate with them. It's going to be a long time before you go to Home Depot and buy a water heater that has a Bitcoin miner in it, where you plug it in and it mines sats, and then maybe they can offer it for literally a quarter of the price because the company is taking 80% of the sats and then you get 20%, whatever. You could do this model anyway, but there's a long ways to get there because you can't build very nice, simple, easy to use integrated systems. I mean, literally for an example, right now, there's no control boards for Bitcoin miners that have Wi-Fi on them. You need an Ethernet. What am I gonna do? Plug an Ethernet in my water heater? You can get my grandma to do that? There's no way. So, oh, the Wi-Fi is down. Oh, I can't heat my shower. So there's a lot of work that needs to be done on the miners. And then from a firmware perspective, ground up design is also necessary for integration into heating applications because what I'm describing here is transitioning from, okay, I want peak efficiency, I want X amount of hash rate. No, I want 85 degrees output temperature. That's my new requirement, right? And you can dynamically change the voltage or whatever to clock around that. But I have a new value set, right? This is my primary product. The heat is my primary product. Maybe that doesn't play out for the mega miners, but on these other industrial applications or home heating, we need to be able to control these systems to say, no, you now serve this purpose, And your secondary objective is to mine Bitcoin and, you know, subsidize my electric costs. And then you rope that all together. This is an image from my friend Dwight. He works, his name's Electrothermal Design on Twitter. Shout out to him, give him a follow. But they're doing the best case right now. This is Zach Baumst's company, Unbound Networks. So these are, I think, 2 S19 boards. There's a power supply in there. This is a home heater. It's just a way fancier version of my Bitcoin miner space heater. They're intending to sell this product, targeting people right now that are kind of in small towns in the rural West where they have propane heating systems. And propane heating systems, you got to truck in propane in a tank once a year, fill that puppy up, right? And it's expensive. So for these people, it literally may be cheaper just to transition to electric heat by itself. But then even furthermore, if you're subsidizing that with Bitcoin mining, you are getting even cheaper heat. You're also hyper decentralizing, physically decentralizing the network in this scenario where you have home heating that are Bitcoin miners everywhere, right? So the physical decentralization, I think, is a key feature because right now, if you shut down Texas, you'd shut down 15% of global hash rate, just if Texas said no more mining, right? So the more physically distributed this is, the more defense there is in that network, that 700 exahash I showed. We want this physically and digitally decentralized. The digital decentralization has to do with the block templates. I'll leave that for another day. But that's kind of all my thoughts roped together. So in summary, Bitcoin's energy consumption is good. It's a feature, not a bug. There's all these benefits: off-grid mining, load balancing, curtailment, heat reuse, so subsidizing energy costs. And then there's all the societal benefits as well. So addressing the FUD, when people tell you Bitcoin mining is bad, think twice, maybe send them my way. I'm still trying to grok this concept as well, but that's where I'm at. And thanks for listening to me today, guys. Any questions?
What do you think about a copper PCB board with graphite and then gold inlaid?
I'm not the guy to answer that question.
No.
Yeah.
Yeah, keep this patient metal, silver.
Yeah.
Silver's the best.
Hyperconductive materials. Yeah. What's up, man?
Have you run like hard numbers on the profitability? So give the example of Minnesota, right? You're kind of like, okay, they're spending, I think you said $600K a year.
60 grand a year.
60 grand a year, okay. And natural gas for heating.
Yeah.
So have you actually run hard numbers on like, okay, if we're to buy a bunch of like, you know, used miners, this is how much they could actually save or how much it would subsidize it, and then, you know, for example, present to them what their savings might be.
Yeah, and the business case for these manufacturing and operational scales, where it's more of, it's not a product you buy off the shelf, it requires engineering, design, and infrastructure and build out. It does require selling that case, right? You need to say, okay, here's the capital expense, here's the return on investment, this is how much you're going to save a year. And ultimately what it comes down to, you can play this model out any which way. I find that, well, whoever pays for the assets, the capital, the Bitcoin miners, which are your largest portion of your capital expense, they need the majority of the Bitcoin mine. So maybe you outsource some Bitcoin miner smart guy to come service it, right? Because the manufacturing plant just wants to focus on whatever they're manufacturing. They don't want to deal with it. So there's some SAT stream split to the guy that manages it, or the company that designed it, for example. Say they take some equity in that Bitcoin mine. But ultimately, whoever pays for the asset, say you get the manufacturing site to pay for it, you know, the majority of the sats need to go to them. And from my quick look, I mean, depending on the power costs and the cost of the miners, if you go old gen, new gen, the return on investment, I think, is in the 2 to 4 year time frame on these systems.
Have you looked much into like PPAs, power purchase agreements, that solar companies work off of?
I have not.
It's a similar thing. I used to work in the solar industry, and like the majority of solar deals are PPAs, and what that is that another energy company will put an array on your roof and then sell you the power,
Right.
and they'll pay for it, and you buy the power from them.
Right.
So largely they're like a massive. They do hardware, but a lot of it's finance. You know, because they're like,
Yeah.
you put that there. I almost wonder whether it seems like what you're describing is.
I think that business model does exist in this scenario. You could come in and say, you know what, I own all these assets. I'm essentially leasing them to you. And then you get a portion of the Bitcoin mined. And to them, they're just like, okay, I don't have to do anything. And my power price just went down, or my heating costs just went down. Yeah. So there's also that model. Depends ultimately if they want ownership. I think, and that is heavily related to how knowledgeable they are on Bitcoin and its future profitability.
Well, it's like
value.
The cash. If they have cash, they want ownership.
Exactly.
If they have cash, they've got like a good commercial rate of electricity and the need, and they'll buy half their heat off of you, and you just sell them heat.
And in that scenario, it's in the designer or the provider's favor because they essentially are saying, oh, this company just wants a cheap new system that lowers their energy prices. But the benefit is to the guy who builds it out, and ultimately 5 years down the line is just raking in free Bitcoin as equity from free hash rate, essentially. Yeah. That's cool. What's up, David?
So I invested in a startup company, and it's a machine that uses thermodynamic energy to capture solar electricity, evaporate contaminated water, and condense it into a condensation tank and provide Wi-Fi connectivity. So add a Bitcoin miner to that, water production becomes much more efficient.
Yeah.
Yeah. So you want to work on that?
It's a cool idea. I'd love to hear more about it. I think there's so many cool applications of Bitcoin miners into traditional power cycles, thermodynamic cycles, heating systems. It's essentially infinite. You just got to lock in, okay, who pays for heat? How often, what's their duty cycle? How often do they pay for heat? Is it 1 hour a day, 364 days a year? What scale, right? And you rope all this in, and I think there are a lot of use cases and applications of Bitcoin miners and for waste heat reuse.
Yeah. I agree. I think I've been sitting in these conversations for a long time, and I think the analogy that you need is that we're going from Atari to like PlayStation. Like the resolution is happening. We're going from 2 decimal points to 8 decimal points, and you guys are figuring out how to get there. Right?
There's a lot of work that needs to be done in the way. Right. On the way, yeah.
I think that's an important analogy that you take with you. Just keep
going down this Bitcoin mining rabbit hole last fall. Learned a lot at the Bitcoin Mining Energy and Summit in Nashville at Bitcoin Park. And I was like, I left that conference, I was like, okay, let's go. Let's use this heat. Come on. And then, I'm talking to electrical engineers and they're like, no, the firmware is a problem, or no, the chip temperature is a problem. The guys that are doing it in the field. And it's like, these things suck. They're made out of aluminum and they're sharp and no one wants to touch them. And the Wi-Fi chip. And yeah, there's all these hurdles to ultimately get to this end state. Yes. Yeah. No, it's fascinating. And that's why I see a fit for it as just a new upcoming industry and application of these machines, which also cements them. This is something someone brought up to me on the phone today. I was talking to a guy in Idaho who builds out these systems. He's done a concrete, small town, like 1,000 people. He said the nearest Walmart's 2 hours away. He did a concrete plant and then also a car wash. They want hot water to clean cars, right? And so he has these systems where the Bitcoin miners heat up the water and blah, 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 blah. And he also has some systems for his neighbors that heat their water heaters in their home. And he brought up a good point to me. He said, when they come after Bitcoin, because they will, the tyrants and the government, they're going to come after Bitcoin mining as soon as they find out really how much energy is consuming, right? If they found out that a 40-foot container uses as much power as a small town, they'll be pissed. But if they come after Bitcoin mining and then everyone in that town goes, wait, you're attacking the thing that lowered my heating bill by 30%? You're evil, right? So you get that societal benefit as well, because if you distribute this hash rate for heat, there's a utility benefit to individual families.
It's happening right now, right? They want to go after unrealized tax gains?
Yeah.
So the reality is happening right now.
Yeah.
It's going to filter down.
Biden is saying like 46% capital gains, like raising the tax. That is insane.
Yeah, so there's a lot of
it will get to every day, but like what we're talking about is like how to apply it in so many ways.
A lot of fear mongering going on, and I think if we can make Bitcoin mining attractive to everyday people, who did I hear say this? They're not no coiners, they're pre-coiners. They just haven't been educated enough yet, right? And so if you can get Bitcoin mining to be seen as a value add, not a negative to everyday people, that will play a huge benefit in the defense of the network, ultimately replacing our monetary system. What's up, Wyatt?
Do you have any ideas or commercial solutions for where space is needed but space is scarce to integrate miners?
Elaborate for me.
In a city where it's heat is needed, but there's not a lot of space to just put up a massive, warehouse for miners. Do you have any idea on how to get miners close to where, heat is needed, so
So I would flip that on you and say Bitcoin miners are one of the most energy dense pieces of machinery you can find. It's an enormous amount of energy. A small new Bitcoin miner, you can overclock them to 6,000 watts. And for context, 746 watts is 1 horsepower. So this little box is like running at 10 horsepower, which is insane. More than Owen's moped. So
I think to add to that, I read an article and I just found it. There's this New York City bathhouse that uses Bitcoin mines to heat their spa water and
Yeah.
their hot tubs and stuff. And that's a pretty condensed area, so I'm sure they don't have a lot of room to work with. But
you'd be surprised how little like number numerically machines you need to deliver the heat load you require. This 150,000 square foot warehouse that I was considering learning about in Minnesota, it's 40 miners,
oh well.
like a server rack. It's like two bathtubs of
Yeah.
immersion fluid.
Wow.
It's insane. Yeah, so they consume a lot of power, which is why they will be vilified. Yeah.
I think it's for other energy sources are scarce, like natural gas, because some of the big cities still have a lot of gas and try to compete with the water heater that's got hundreds of thousands of BTU, and it's like this big, and it's got hundreds of thousands of BTU, but it's got a gas line going through it.
Right. Yes.
So that's where it's really hard to compete with the density of it in a big city. Is like you could have hundreds of thousands of BTU.
Yeah, and
water heater, but you have to have gas to it.
hydrocarbons are orders of magnitude more energy dense in
It's hard
terms
to
of
compete with that.
than electricity. Yeah, exactly. Like the gasoline you put in your car, your engine, like all of the potential energy of that fuel. Like if you were to mathematically say, okay, how many?
Versus an electric car.
It's like
Massive.
your combustion engine car is like 25 to 30% efficient at turning that gasoline into motion. Your electric car is like 90 something. But the electric car is way more because batteries aren't less energy dense. That's the value add. Your fuel, your hydrocarbon fuels are literally orders of magnitude more energy dense. So oftentimes, I mean, if you have a good tap line into natural gas or oil or whatever, it can be cheaper in those scenarios. Yeah.
if miners are tending to like get faster each year. Just like, is that like is the energy to heat output going to be less and less? Do you think?
This is a great question, and I'm still trying to understand this concept better. I'm by no means an expert, but as you go smaller in nanometer processes, I don't know if you're familiar with those, but like your phone went from 7 nanometers to 3 or whatever Apple's at. That means the transistors are getting smaller, and that's more efficient. It takes literally less energy to move electrons because they're going less distance. And the trade-off is you get way more efficient, way more processing power on a die, right? You can get more hash rate. But because the transistors and the circuitry is so much closer, you actually get what's called leakage current. Scott, who developed the BitAx, talked to me about this. So at high temperature, you have more motion. Things are moving around, vibrating, you're warm. You can actually get electrons leaping between these traces, and it causes errors. And so these smaller nanometer, more efficient, higher hash rate chips actually often are required to run cooler so that they don't mess up. And so I was looking at, spec sheets of like Bitmain's ASIC chips. It's like the S9 chip can, on its spec sheet, it can get way hotter because it's an older process. So it's kind of a trade-off. That was what my article with Brains was about. I think we're going to see Moore's law asymptotically kind of level out, and your year-to-year improvements in hash rate, the newest chip, it's not going to be worth spending $8,000 on the newest miner when it's like, we went from 200 watts per terahash to like 80 watts per terahash, then to like 20 watts per terahash, and now they're going from like 18 last year to 15 year to year. So it's marginal, and I think we're going to see a plateau where those gains don't warrant you going out and spending all the capital expense. And then the question just becomes, okay, we're not really upgrading the machines as often. Maybe we can reuse these older nanometer processes, or maybe we can find a way to increase the temperature that these can operate. And what I argued in an article with Brains recently is maybe the case makes sense, and I could be wrong, but we'll see like a bifurcation, a split in ASIC design intent. Well, you'll have the mega miners, the riots, the marathons saying, you know what, I'm going to spend X gajillion dollars to get 5,000 of the newest S50s or whatever. And they're the most efficient machines. It makes sense. I have this locked in energy price. But for this untapped market that I see with heat reuse, maybe it makes sense for Samsung or TSMC to say, yeah, we'll dedicate a team that actually just takes that 5 nanometer process from 2 years ago and tries to clock it up to 110 degrees Celsius. Because then I could sell it to all these guys, right? And
It's like semiconductors are kind of standing in the way of that, right? Like,
yeah, I mean, it gets down to the semiconductor level, and ultimately, it's like a Goliath of an operation. When you design an ASIC chip, it's the circuitry to programmatically perform the mining hashes is hardwired into the chips. So there's a lot of capital expense and build out required design teams, years of development to get ASIC chips.
I can't wait to mine Bitcoin.
So we'll see what happens on that front.
Also seems like Moore's law is like inevitably going to just end, because like the physical realm that you could, the amount of transistors you can fit on a chip, it has to, like, there's gotta be a physical limit.
Who knows? They said we wouldn't.
Yeah,
They said that we wouldn't find any more oil too. So
That's true.
Are you guys digging into the power law thing that's happening right now? Like,
I've seen the posting about the power law.
With Fred.
Yeah, Fred Rubio
Yeah.
and the other guy, Giovanni.
I don't know if it's still streaming.
It is, we're still going. I think so.
Cool. Yeah, great questions from everyone. So it's kind of all coming at me really fast. It's all streaming to me. I see this vision of heat reuse and mining, and it's like, okay, what do we got to do next? What do we got to do next? So I appreciate you guys listening to me today. I'm ultimately trying to turn this into a business, focusing on that operational symbiotic relationship scale. That's that Exergy. That website is going live soon, but it's like, how can we basically connect heat consumers and heat producers? Let's connect them. We got a deal, baby. Let's go. So, yeah.
Sweet.
That's all I got.
Cool. Well, thank you so much, Tyler.
No problem.
Yeah, so that's it for this meeting. We do monthly meetings last Thursday of every month. Love to see new faces.
If anybody's not in the Telegram, wants to be in the Telegram, you can scan that QR code.
That's where we post all our updates and yeah. But yeah, through the summer, we just got to see how the school works with just like walking the buildings. But either that, we'll have some Zoom meetings. We were just talking with the author of a progressive case for Bitcoin, Jason Mayer, and he's willing to speak for us soon. And he's going to send us a couple signed copies of his book. So that's something coming up. Yeah. That's
Pretty much all we got.
Yeah.
Thank
You guys
you
so
all
much
for
for
being
coming. Really appreciate it.